All right, what day are we? We are a Wednesday. So we're continuing off the work that I was doing yesterday on matrix multiplication. Um, because I was really tired. I think I only worked on this for like 30 minutes. Um, but I guess as a refresher, we have a naive implementation of matrix multiply, and then we have this, I guess, more cache aware matrix multiplication, right? So by simply changing these two for loops, exchanging them, we get a much higher speed up in performance. So if we go like this, this was comparing templated versus the non-templated version, and we see that it is the same. In this case, when you template, you just basically generate multiple functions are generated at compile time. Whereas if you have it passes an argument, and it's the function. It's the same function, right? Instead of having multiple instances of templated functions, you have the same function, and you'll use the arguments inside the function call. Now it depends on how you use it, right? But in this case, it doesn't really matter whether you template, like you pass in more arguments. I guess there's more values that are passed at runtime, but that's like really negligible. But really, what we're interested in. So in this case, I guess like we don't need to template it. We'll just do that, and then there is a more cache-aware version of matrix multiplication. So essentially, what is happening, and maybe I can pull out my. I really want to do this in Obsidian matrix multiplication. And I was also trying to visualize this because myself, I cannot really. Can I close all these, please? Close these plugins. Oh, we have something. Matrix multiplication compute. The simplest implementation. Yeah. Multiplication. What's happening? And then I had a drawing, right? So imagine n by m matrix. Should I redo this? Maybe I should redo this. Like the way Mr. Siboam drew it was really good, and this guy works at Entropic now. Yeah. Why does his look so much better? Okay. So what we're going to do, and he has the squiddly stroke style slop. He has it very sloppy. I guess that helps, huh? Okay, we're gonna do it like very seriously this time. Okay. All right, that looks a little bit better, huh? And then let's draw our. So he has a sloppiness like this. Okay, he made it very sloppy. I guess we can make it very sloppy too. Actually, I don't like it that sloppy though. Just need to make sure it's square. Okay, so this is a square. This looks like a square. I really enjoy making these diagrams though. Okay, so we got this matrix. Okay, this is gonna be a template. Let's group selection. Okay, and this is going to be a template. So we have a n by m matrix, right? And then he did like an arrow. This is rows, n rows, and then k columns, and then multiplied by a, so this needs to be rotated like that. K rows, let's take the add symbol, this red, or here's columns, k by m matrix, let me make this drawing better, equals, so we keep black, a n in this case, what is it? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9 by 10, and this is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 9 by 10 and 10 by 9, and you should get a 1, 2, 3, 4, 5, 6, 7, and 10. So you should have a ungroup, a 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 10 by 10. It's the attention to detail that matters here. All right. So a 9 by 10, this is a n by m matrix. And how do you make this? K by m. N by k equals alright, that's just how, so if you multiply n by k matrix, so the inner dimensions must be identical for matrix multiplication to work, and you multiply these together, you'll get a n by m matrix. And the way the computation is done is by looking at, so that I was explaining this yesterday, but essentially this first value will be given by so maybe this is more obvious. So this value is equal to, maybe like orange. And background. Oh. This is equal to this. Wait a second. Okay. Why am I like so stupid? This is what happens when you're stupid. I literally did the exact same thing. It's the row times the column, not the. Else it doesn't match. I was like, wait, something's wrong. Right? This is how they match because the width is exactly equal to k. Right? The width of this vector each matrix value, each value of the matrix multiplication is a dot product between the ith and the jth. And the jth column from the second matrix, right? Alright, so I hope this makes sense, and probably wanna, we can delete this. And you can make the words bigger. Or a specific matrix multiplication. This is a dot. Can you see my dot? Actually. Right, and so that's how we compute. Dude, why does this look better though? Okay, I guess I've sort of replicated what he did, but I have more. No, I basically have the same. I will give him a shout out. And maybe I can get rid of this. This feels kind of naked though. I love the way he drew this. Oh. Wait, did I just copy what he did without? I swear, I didn't even realize he did exactly 2 as well. But here's what I think I'll do to make it better. Yeah, that looks really good actually. That looks really good. Group. Okay, we'll do like the third one. Group selection. This should move a bit more to here. What is it? Okay. So this is how matrix multiplication is calculated, right? So what you do is like, you can imagine that we are just doing a scan over like this first value is going to be computed by multiplying the first row and the first column. And the second value will be multiplication between the first row and the second column. And then the third at row 1, column 3, or row 0, column 2, because we're zero indexing, then it'll be a dot product between this vector and this vector, right? And dot product is essentially just multiplying the first element of the vector with this first element. The length of these two vectors must be the same. That is why when we matrix multiply, it needs to be n by k multiplied by k by m, right? Number of rows, which determine like the height of this column, should be equal to the width of this column, which is the equal. In the first matrix, it's n by k, because k is how many columns, and how many columns determines the width of this vector. All right, all this to say that we have matrix multiplication, but there is, I need to discuss sort of how we lay this matrix out in memory, right? So if you look at how memory, like, what is memory? I assume there's some basic understanding of how memory works. So maybe we can have a small example here, right? So every time you create a variable, int x equals 5, and then you can let's use namespace because you shouldn't do this in production, but I don't want to like write std count, so I'll just write count cout, and then let's say we want to we can print the memory address of x, and then let's use warp and gem memory. Yeah, so this is where the variable x, the memory address of variable x is. This is the virtual memory address, not the actual physical memory address, because computers nowadays in the operating system use virtual addresses. I think that is correct. Let me double check with ChatGPT. I'm pretty sure that's how it works. That prints out the virtual, correct? How do I get what do you mean by that? Yeah, isn't that what virtual address is? Virtual addresses essentially abstract away how physical memory is laid out, right? So if, I guess I can show you guys. I gotta make sure it's a public node. Basically when I was in video, this is like how I learned it. Hemel taught me. Hemel was like my manager, and then if you look at CPU architecture, like I have a drawing of this. Essentially, you have your CPU, then close to the or your CPU. If you look inside what a CPU is, you have your ALU. You have registers. You have like ALUs that do the computation, and you'll have your L1, L2 cache, and then you'll have your RAM, right? And that's your memory. So which note is that? Memory model. Yeah, pretty sure it's this. Show 2023. No. Yeah, something like that. Okay, I guess I only it's still in my private note. But yeah, you have your CPU, and your CPU talks to your RAM. And inside this CPU there's also ALUs, right? So in practice, your memory can be instructions, it can be data, but nowadays there's virtual memory, because imagine before you would have to say like, oh, at memory address 1032, you would put a variable in there, right? And you have to keep track of it. And then imagine you have another program running, and you use absolute addresses, and you specify 1030. Like you're not aware of you need to be aware of like what process is using what memory address, right? So the operating system, by having virtual memory addresses, or by having processes use virtual memory addresses, sort of abstract away that problem of having to worry about what which processes are using what memory address. So you end up, as a developer writing your program, you can just use virtual addresses, and then your OS will take care of translating that into some physical address through so that's your virtual addressing. And there's also caching for that. It's called a translation look-aside buffer. Your TLB will be a cache of the mapping from your virtual address to your physical address. And if it doesn't exist in your TLB, then that will be a page fault is when paging is the process of, well, it would just be a cache miss if you don't hit your TLB, and then it will look inside your page table. All right, and then if it's not in your page table, then you have a cache miss. Right, I think that's how it goes. Page fault. That's not page fault. Page fault. Page fault is an exception. Exists in secondary. I guess the term is address translation, right? Translating a virtual address into some physical address to know what value you actually read from. Okay. Okay, so we were deviating, but I was essentially trying to explain that all of these variables you use, right, under the hood, how your computer works, there's RAM. RAM is memory. Memory is, at the end of the day, it's just a temporary storage for your bits, right? Your zeros and ones, a place to store your data, right? That's what memory is for. And the way this data is stored is you will be able to address it. So there's like byte addressing. So this memory address is first of all a virtual address, because the operating system sort of will take care of, like, that's not an address that actually exists on your computer. That is a virtual address, and then the OS will translate that into some physical address that you as a developer won't have access to. If you did programming with like a nucleus board or like some lower level microcontroller, you can just you won't have like the OS abstracting this away. Okay. If we run this again, you end up with like different memory addresses, right? And if an array is just a pointer to, so actually when you initialize an array like this and you print x, that will also just be a memory address, and that will be x is actually just a pointer to the beginning of the array, right? So you can see that this is also just some value, and in this case, if you increment the pointer, what will happen is so this is in hex, right? So so an int is 32 bits, so it would take 4 bytes, right? So what we should see when you do x plus 1 is it will shift the pointer by 1, and the amount of shifting it does is the current pointer plus the size of each of these elements of the array. Okay, so in this case we want to plus, so this is however many, this is the number, and then we need to add it's in bytes, so we need to add 4 to this. All right, so then we should see the first number and then that number plus 4. Wait, what's happening? Yeah, so that's what happened. I don't know what happened. Oh, it's because I forgot to, I should have done n. Right. And segmentation fault will happen. So if you did x equals 5, and then you have this memory address, right? So you can have pointers. I mean, this is just the very basics of how pointers work. So you could have a pointer to this variable, and then if you print p, that will be equal to the memory address of x, right? So these are the same, but now if you want to shift the pointer to the next address by doing p plus 1, that also works. But then now the referencing a pointer is simply reading the value at that memory address. So, but in this case, we will end up with some sort of segmentation fault because or it can be garbage. I guess in this case it is garbage. But I think maybe if you did like p plus 100, well, we also have ownership over that address space. So I guess the computer lets us, the compiler lets us. I'm actually shocked that this is not. Why is this not a seg file? Yeah, I think this is undefined behavior, right? But essentially, you're not guaranteed to have ownership over that specific memory address. So actually, what we can do is, if you could also just do like a pointer, p is equal to this value, and then if you print the value of p, and then end it. Type long. how is this not the right syntax? I want to recompile and C first. Yeah, but this should compile, right? Okay, I guess in C++ you can't do it. You can cast this to be a, because this will trigger the segmentation fault, I think. Yeah, because it's just some random memory address that you don't really have ownership over, right? You and you're trying to read from that memory address. That is what a segmentation fault is. So back to the so when you allocate, so let's say we allocate an array of size 1000, count x. So what will happen is the this will be the beginning of your x, right? The way I sort of visualize this in my head is create new nodes or Xcolor draw, create new drawing. The way I sort of visualize this is, I guess I kind of visualize it like this. And then you just have, like, imagine these are just a bunch, these are bits, right? Like this could be 0, it could be 1, etc. And so these are the values, and then these are like the memory addresses, right? So you start from 0x00. This is memory address 0x00. Now, this is actually not quite correct because data is actually stored 1 byte or 1 in words, right? So yeah, I think it's byte level addressing, right? So address 0, and then address 1, there's a difference of 1 byte. So there's actually 8 bits. 1, 2, 3, 4, 1, 2, 3, 4. Right? So is that true? So if you do x plus 1, okay, this sets the value of x. Yeah, so you add 4. Does that add 4? Hello? What the hell is going on? Why is it closed? So interesting, we printed x and we printed O. Right, so the beginning of the array points at this memory address, and then if we increment the address by 1, we actually get this address, and this address is a difference of 4. Because in this case, actually, the pointer under the hood, this actually calls x plus 1 times size of int, where x is some memory address, and then size of int will return the size of int as the number of bytes, because what will happen under the hood is automatically your fp your int takes up 32 bits. So you can imagine when you increment it by 1, you will actually increment it by 4 bytes. And if you don't believe me, what we're going to do is use another type. So a car takes 1 byte, right? 0 to 255, so 2 to the 8. Is that correct? 2 to the 8 minus 1 is 255. Wow. I know my stuff, man. Okay, so if you do this, then, and let's clear this. So in the case of a character, if you print, what's happening? Count x. Hello? Why is it not printing? Oh, can you have an array of... Why is it not printing? I'm kind of confused. Is it something with characters? I guess it treats. Yeah, I think CL treats it as a string in this case. If we set it to like 1, yeah, that also treats it as a string. What's a data type that uses? It's only a byte. Or like array of booleans. Isn't the bool just 1 bit? How many does a bool in C++? Because a bool should be just 1 bit, right? But the smallest you can have is 1 byte, no? Yeah. The CPUs are aligned in a byte, yeah. Word add, what's word? Word. Yeah, here's the example, right? So your addresses, at each address, you store 4 bytes. You store a word. So yeah, you don't actually store Okay, so then how does that work? And each does it store a bit, a byte, or word? Say between address 230 and 231. I thought it was a byte, but yeah, like you store it by word. But in which case, I'm pretty sure it's word. Is this? Yeah, byte addressing is supported because of virtual addresses, like on the actual hardware. Is it word addresses? And then there's some sort of translation. Like, how does that work? Yeah. Okay. So what's the point of words? So what is the point of words? I learned in school. Is the size? Yeah, your register can store 32 bits or 64 bits. And so that's why in a 30, if your register is only 32 bit, you can only address like use an address of up to 32 bits, which might not be enough. So we have 64-bit addresses, and then now with virtual addresses, we can also access like more. You have more space because you can reuse the same virtual address for two different processes as long as you have the correct translation. Boom, genius. Okay. All right. So back to what I was explaining. If you have a bool takes a byte because you cannot have bit addressing. The smallest, each element of the array can only must take at least a byte. And okay, let's see this example, why it was byte addressing or memory. Is it memory aligned? So why is this one not good? Because let's see here. Because you have a byte and it's not memory aligned in the sense. Well, first of all, when you do a read, you read 8 bytes at a time. Right? In this case, it's 1. So this is 4 bytes. So this is 4 bytes, then 8 bytes, then 4 bytes, right? And I guess it's not, depending on how the struct is set up, right? Because like there might be space that is wasted because it's 4 bytes, 8 bytes, and 4 bytes, as opposed to 4 bytes, 4 bytes, in which case it's about like what's the word? Like it needs to be addressable as multiples of the size of that, right? So for example, if some struct takes in 12 bytes of data, then it must be stored at a memory address that's a multiple of 12. Is that true? And also because you read it in multiples of 8 bytes. is that true as a general statement? Like a struct that is 7 bytes requires 7-byte alignment. Where does the byte alignment requirements from? Yeah, so generally there are these alignment requirements, right? So your primitive types, your unsigned, or your integers that are 32 bits, or your longs which are 64 bits or 8 bytes, generally must be stored at addresses that are multiples of 8, right? Or for long and multiples of 4 for your U32. But imagine the case where the struct is created at like some multiple of 10, right? So it starts at 0, and then from addresses 0 to 4, right, where so each address is 1 byte, right, takes up a byte because we have byte addressing in modern compilers. Important. Byte addressing is the norm. All modern hardware support byte addressing. Then what is the point of word? Words tell us how long, words for how many bits a given register can store, and that has implications in how much 64-bit architecture. Like, we just say a word is 32 bits. What's the definition of word again? What is the definition of in computer architecture? What is the purpose of, I guess because like when a register reads data and it reads you copy a word, you don't copy a byte, right? Because a register can load in can store 32 bits, i.e. word. In 64-bit architecture, we work with words, with double words, right? I guess it's a word is a standard unit of data that can handle a process, that a processor can handle at a time. So when you read 8 bytes at a time from your memory to your cache line, that's 8 bytes at a time, which is a word is 4 bytes, so that's so it's a double word. Oh, it's just a double word. Cache line. Oh, it's actually 64 bytes. Okay. So what I was trying to explain was memory alignment So here, if you store your struct as a multiple of 0, and then you store a, right? Assuming that you're trying to store this in contiguous memory, so U32 will take up 4 bytes, right? And then you're at byte number 4. But U64 is 8-byte addressable, but 4 is not, or like that address 4 is not a multiple of 8. So then you'll actually waste 4 bytes of empty space just to gap, so that the B member variable can be addressed as a multiple of 8, right? And that all further has implications down the line when you try to do reads. When you do reads and then you have your caching, do you end up with like having to do 3 reads instead of 2 reads? Well, you would read, so that would take up what, 4 plus 4, so 8 plus 8 plus 4, 8 plus 8 plus 4. I guess we can actually see the size of it, right? 16, so 20. So it would be the size of 20, but if you had it like 4 fours, that, and that would be the size of 16. If you had like this would be 16. Is that true? Struct long, or int a long b in C. I don't know how to define a struct. Int a, it's probably like a quote like this, right? And then so this, I mean, if you just sum up, now it's 4 plus 8 plus 4, which is 16. But is it going to be 16? No, it's going to be 24. Is 8 plus 8 plus 8. But if you arrange it like this, now it's 16. So it eats up, because I assume that the struct, and then I think there's a keyword, right? Align as. What is the size of food? So I'm a little confused as to why can the struct not end as a multiple of 4? Like, does it always have to end up as a multiple of 8? Right, so 8, address 8 to 16, and then 16 to 20. Why does the oh, okay. can the packing pragma pack. Huh, this is interesting. I didn't know this stuff. Okay, I mean, I kind of knew, but just a reminder of like how memory alignment works, right? So you want things to be memory aligned. Memory aligned just means, like, what's the definition of memory alignment? Right? Byte aligned means your data must be so if there's some data structure that like a boolean, for example, if you create an array of booleans, right, each element of the array must be byte aligned. You can't just like have it at bit 1 and then bit 2. Like each address must be addressable via, like, the difference between address 1 and 2, each address stores a byte, right? So you can't have bit addressable values, and so therefore each boolean must store a. But then how does a bit set? Because you can store a bit set. This should be like 2, right? It takes an 8. 4, like 8 bits, like this should be 1. Huh, really? Oh, I guess, is it like how vector is defined as, if you could do a size of vector, that will always be, there's a pointer to the beginning, a pointer to the end, right? And then a pointer, there's like 3 pointers, and each pointer is just some 64-bit number, because we're a 64-bit architecture, which is 8 bytes. So 3 times 8 equals 24, right? So size of vector, and that should be 24. And if you do long as well, it doesn't matter because they're just pointers, right? Because you have beginning, but yeah, point at the beginning, point at the end, and what's the other one? I guess point to the unused. Okay, that's nice. Why do the methods not occupy any space? compile time. Yeah, they're stored in code. This is why people hate C++, right? Because it's like abstracted away and you don't really know what's going on. Okay, anyways. So we understand how memory works, right? Memory is storage. Memory is RAM, right? Memory. I mean, you can use cache to store data as well. Registers also store bits, but memory is sort of. If you look at how coder is organized, you have your data stored in memory. I mean, code is also technically stored in memory, but you also have instruction cache, right? But what happen is you're gonna store your matrix or your array in memory, okay? So and then you'll be able to address it. But now when you want to do computation on it, what will happen is you will actually load the data from memory. So this one, CPU architecture name. What? Yeah. So what will happen is like you will copy. There will be instructions to move from memory into your registers, and then there's going to be your ALU that will do operations like adding or subtracting or multiplying, whatever, right? And you can't just like directly do computation from memory. You need to load it into your registers first, right? That process of loading from your memory into registers is slower, right? And also, you want to write that back into memory, right? So actually, when you do, something as simple as like a 100 and I equals 0, I less than 100, I plus plus, AI, a is equal to AI minus 1 plus 1, for example, right? You can do something like this, right? You do something like this. Like under the hood, what actually is happening is AI is stored in memory. You will read AI from memory. If you haven't read it from memory, it will, or first of all, it might get cached, right? So you need to load it into your cache, and then there'll be an instruction like you'll load it onto your register, and then it will increment. You have to load AI on this one into your, one of your registers, increment it, like do call an instruction that adds, right, into, or like their instructions to add, and then you write to AI, where and then either you do it at a register level or like you move it back into memory. But the compiler is smart enough to do some optimization here, so we can actually do I have object dump? Object dump. Oh, we can. Oh, I have object dump dash a.o. are object files. Object files are like basically the translation units, right? As assembly? No, right? Object files are essentially translation units that that should get compiled into assembly words. Did you compile code? Okay. Is it object file first or assembly file first? See, at work I use Bazel, and I just do like there's a flag to do debug. I don't know how to do it. So you just do the output object dump source status. Dash disassemble. Okay. I see. So this is the assembly code. So the object file is just, if you did like main dot like this is just machine code, but object dump does how does know the assembly code. Yeah. Alright, so object files are sort of compiled translation units. And then there's an assembler that will link if you have like a main that uses a bunch of these libraries, and there's going to be a linker. In the linker's job, there's a few things that the linker does. It sort of like does relocation. It relocates addresses and it resolves labels. There's two things that it does, right? It resolves addresses and object files to account for the code is starting an offset other than 0. It relocates the addresses and it resolves whatever symbols were not used. It resolves these labels, so like functions that you use from other files. variables, and this is where you find the actual implementation. Okay, interesting. All right, so you can look at the assembly, and what you see is these are, okay, I don't know how to read this, guys. You learn how to read. I mean, we could also just do it in Gabo. Compile Explorer. Say going downwards and increasing memories. Guys, this is getting complicated. I just wanted to do multi-check multiplication, and now I'm going down this rabbit hole because I need to understand this stuff. Damn, I didn't get very freaking far today. Okay, I'm gonna end it here today. We're gonna continue hopefully tomorrow.